Okay, so today we're looking at 9G, Eulerian trails and circuits. I hope I'm saying that right. So Euler's work led to the creation of two concepts. These relate to the edges of traversable graphs. So looking at yesterday's work, okay, we've got traversable graphs, so a trail that includes every edge. And we're looking at a trail and circuit with touching every edge. So this is a little fun acronym, EEE, Euler every edge. So that's how you can remember it. So an Eulerian trail, so actually I'll get my highlighter, they're already bold, a trail that includes every edge of a graph. Okay, the trail starts at one vertex and finishes at a different vertex while traveling along every edge once. Okay, every edge once again. So obviously the difference between a trail and a circuit you have to return to where you start, and a trail you don't have to. Okay, but the Eulerian part of this is the fact that you must touch every edge. Okay, now the rule to trace an Eulerian trail, so the graph must have exactly two vertices of odd degree. Okay, so remember two vertices, so meaning two dots or points like A and B. Okay, must have exactly two vertices of odd degree. So odd degree here, meaning that the part or the edges that connect to them, it has to be an odd number. So it might be 1, 3, 5, 7 edges that touch that degree. Okay, now it can have more than two vertices. Okay, your path or your graph, you can have lots, but you've got to have exactly two of them that have an odd degree. That's what this little part means. Okay, so exactly two of those vertices in your graph have to have an odd number of edges that touch them. I'm going to rub that out because it looks really ugly. Okay, the other one is start at one of the odd degree vertices and finish at the other. Okay, so again, we're looking at the odd degree vertices, and you've got to start at one and finish at the other. That's how you can make sure they touch. And very important, do not repeat edges. Okay, so for this example, we've got 3 vertices, so that's fine, but exactly 2 of them have an odd degree. So this one and this one, they only have one edge that touches them, and one is an odd number, so that's good. Okay, and you're starting from one of them, so starting from here, and you finish at the other one, so that does this one. And do not repeat any edges, so you can go to your other one and then go to that last one, and you haven't touched the same edge twice, so we've done that correctly. Okay, so that's what we call an Eulerian trail. So moving on to a circuit, like I said, the same thing, except you start and finish at the same one. Okay, so Eulerian trail starts and finishes at the same vertex. Is a circuit. So to trace an Eulerian, I'm saying it wrong, but anyway, circuit. So all vertices, doesn't matter how many are in your graph, but they all must be of even degree. So an even number of edges must be touching them. Okay, so 2, 4, 6, 8 must be touching your vertices. You can start at any vertex unless otherwise instructed, but you must return to the starting point, and you must not repeat the edges, because that's what makes it Eulerian. Okay, not repeating edges makes it an Euler thing. So you can see with this one, we've got 3 vertices here. Okay, but all 3 of them have even degree. So this vertice has 2 edges, this vertice has 4, and this one has 2. So 2 and 4 are even, so they've got even degree, so that one's good. We can start at any vertex, so we're starting at this one, and you must return to the starting point. So we're also finishing at this one. That's what makes it a circuit. Okay, and you must not repeat any edges. So with this one, you're starting here, going here, there, and you can come back. Okay, you're not touching that edge from before because they've got that even degree, so you're not going to ever touch the same one twice. Okay, so hopefully that makes sense. You've got to really follow the rules, tick them off, make sure you're doing it correctly, but that's how you can tell whether a graph is Eulerian trail or an Eulerian circle, a circuit, if they're returning to the starting point. This is important here, so note, if the graph has more than 2 odd degree vertices, neither an Eulerian trail nor an Eulerian circuit exists. Okay, so that was back up here, 2 odd degree vertices. See here, let me get another colour. Okay, here, it says exactly 2. Now that means exactly 2. So that's what this means. If it has more than 2, then this Eulerian thing doesn't exist. Okay, there are a couple of applications here. So why bother looking at this or learning about it? So a couple of examples are a postman delivering mail without travelling along any street more than once. So that would be a good thing for him. If you're visiting the zoo and you want to go visit everything, but you don't want to retrace your steps because you want to minimise the distance you walk. Or you might be shopping in the supermarket and you want to visit particular aisles, but you don't want to go over the same aisles. Okay,